In this lesson, we're going to take a look at gaseous diffusion. Now, it's simply called gaseous diffusion, as we'll see with gaseous centrifuge, because it uses uranium hexafluoride at a temperature above 135 degrees Fahrenheit such that it turns into a gas, and the properties of that gas are what gives us our separation. Now, gaseous diffusion relies basically on one particular component, and without this component, there is no separation at all. And this component is called the diffusion barrier, and we'll talk about that here in a little bit. But let's take a look at, if I had a whole gaseous diffusion unit, what would it look like, and basically how does it function? So if we look right here in this two-dimensional drawing, we'll see that we have a high pressure input with our uranium hexafluoride. Then this dotted line shows a low pressure area that's on the other side of a diffusion barrier. Now, the diffusion barrier is what's going to let us slightly enrich, and I mean just slightly. This is not a very efficient separation technology. That diffusion barrier will allow us, along with that pressure differential, allow us to get slightly enriched in uranium-235 compared to what our input stream is. Okay, now we have two things coming out of our gaseous diffusion chamber, if you will. We have our slightly enriched product stream, and then we have our depleted stream. Okay, so just like with the very basic mass balance that we looked at, we have our feed has to be the same as our product and our waste. Now, why do we get slight enrichment because of that porous barrier? Well, it has to do with the difference in mass and corresponding difference in velocity of those two different particles, in this case, uranium-238 and uranium-235. So what's happening is if they're at the same temperature, but they have different masses, they're going to be moving, or they're going to have velocities that are slightly different. And it's all dependent upon how massive they are. Okay, just like with what we saw with EMIS, where their kinetic energy, even though we put them through the same potential, meant that they were going to have different velocities. The same is going to apply here. But instead of applying something like a voltage potential, by heating up the mixture of uranium-235 and uranium-238 hexafluoride, if they're at the same temperature, they're still going to have correspondingly different velocities because the temperature corresponds to their velocity. Now, we're going to be pushing them in at a high pressure. We want low pressure on the other side of our diffusion barrier in order to give the particles a reason to go through the barrier at all. If it was at the same pressure, there wouldn't be anything to draw them, if you will, through the diffusion barrier. So we need to have two different pressure zones, and the gas, our mixture, is at the same temperature, which means not only are we going to have the different masses, but we're also going to have different velocities that correspond to those masses. So how do we determine how good our separation is going to be, given that we understand how to make the diffusion barrier? Okay, well, the difference between them, so if they're all, if they're at the same temperature, we have these two different equations, right? We have different masses, we have our velocity terms, and we have our 1/2 term. Basically, this is their kinetic energy, 1/2 mv squared. So what we want to do is we want to look at, all things being equal, if this equation holds true, and it does for the most part, we can say that the velocities are going to be proportional to the square root of the ratio of masses. So we can say, okay, well, the difference in velocity, that's going to tell us how fast they're going to get through the diffusion barrier, right? Because the ones with the higher velocity are going to tend to migrate through it faster than the slower ones. We can see that that's basically just the difference in mass. And if we do this really basic calculation, we can see that the difference in mass is about 1.0043. And that, in turn, is our separation potential alpha. So I know we didn't talk about separation potentials with EMIS or even enrichment potential with EMIS because at a theoretical level, it can be 100% efficient. So you'll have all of one in one bucket and all of the other in the other bucket. But here, this is, a very simple mathematical way, again, idealized, it's not perfect, of being able to determine with gaseous diffusion what's going to be our separation potential, what's our alpha. And this is how we find it. Again, it's really pretty straightforward. Now, if we look down here at the bottom, we can see a three-dimensional image. Oops. We can see a three-dimensional image of our gaseous diffusion chamber, where we have two different things. We have basically one in the center. Okay, so if you think about it like a donut, we have our input in the center of the donut, and all the way around the input is our gaseous diffusion barrier. So the outside of the donut is going to be our low pressure area. Okay, so we have an input in the middle of the donut, we have an output in the middle of the donut, and then towards the edge of the donut, we have our product stream. Okay, so our enriched section is coming out from a completely different place than our input and our waste stream. Hopefully that makes sense. Now, our gaseous diffusion barrier, it needs to be pretty specific in order to work. Now, uranium hexafluoride is extremely reactive, okay, because it's got fluorine on it. And this is regardless of whether or not it interacts with water, which makes it even worse. And we'll talk about that in a different lesson. It's highly reactive. So we need some kind of material that it's not going to react with, so it's not going to corrode it and turn it useless. And we need to kind of look at, well, what are the dimensions where our barrier's got to have? It's basically a hunk of material with a whole bunch of really tiny holes in it. So we need to look at, okay, well, how big are the holes and how far are they separated? And those two little parameters are basically the stopping point or the wall for a would-be proliferator trying to use this method. They would have to either figure that out on their own through some math, some engineering, and some trial and error, or they would have to get that barrier design from somebody. So if we take a look here at the top, we have, again, a very stylized version of what our diffusion barrier would look like in multiple layers. So here are our atoms of whatever our diffusion, or molecules of whatever our diffusion barrier is. Okay, and this is looking at it from, if I'm at the high pressure side and I'm looking at the barrier going into the low pressure side, this is kind of what it would look like. And so we have these molecules or atoms, they don't perfectly line up, so there's a little bit of gaps in between them. Now, for this particular example, the molecules look like they're about 100 nanometers wide. It's not entirely perfect, but sure, we'll call it 100 nanometers. And the spacing between them, where they don't overlap, is about 25 nanometers. And imagine that this is one layer, and then there's another layer stacked in front of it, another layer stacked in front of that, and then another layer, and so on and so forth, for a given thickness of material. The size of these holes and the path, the distance that your molecule, that your UF6 has to travel to get from one side of the barrier to the other, that determines basically how good your separation is going to be for a given stage. So you need to pick the material so that you get these holes that you're going to need, so that you get the appropriate path length, so that for a given pressure differential, you're going to get a certain flow rate through that barrier. Okay? And again, as I mentioned, you have to make sure it doesn't corrode. UF6 is some nasty stuff. So you want to make it out of something like nickel or aluminum oxide or some other material that it's not going to react with. Not only do you need that for your barrier, but for your whole system, right? Because it's not just your gaseous diffusion chamber by itself, right? You've got to have something to move that UF6 gas through the system. You need to be able to heat your UF6 up to the temperature to where it becomes a gas. So you need piping, you need heaters, you also need pumps, right? Because you have to generate two different pressure areas within your diffusion chamber so that that migration happens, through your barrier in the first place. So your primary pieces of equipment and these all have to be pretty much corrosion resistant to UF6. You've got your diffuser, and then you've got your pumps, your compressors. This is how you're making that pressure differential. You need motors to run them. You need cooling systems, right? Because you're generating, because it all has to be above 135, you have a lot of heat. So if you put this stuff in a building, it's just going to keep heating up as none of that heat can get trapped. So you want to make sure everything's at a constant temperature. So you need to get some way to get rid of excess heat. And then all the piping that goes between the different, not only the different units in a stage, but between the different stages in your cascade. And that's pretty much, gaseous diffusion in a nutshell. It's, it really relies on very specifically that diffusion barrier and that pressure differential in each individual gaseous diffusion chamber. So I think the next technology that we're going to look at is gaseous centrifuge. So we're going to see why nobody really uses gaseous diffusion anymore. If you look at its alpha of 1.004, you can see that it's not that good. So with gaseous centrifuge, we're going to see the differences between them and why everybody really prefers gaseous centrifuge instead.